Organic chemistry reactions, high level 2. Reactions of halogenoalkanes, nucleophilic substitution reactions and mechanisms. We'll do an overview of the nucleophilic substitution reactions first. Halogenoalkanes undergo nucleophilic substitution when they react with a nucleophile. A substitution reaction is one where one atom on a reactant is replaced by another atom from the second reactant. In a nucleophilic substitution reaction, a nucleophile replaces the halogen in the organic reactant, and the halide ion is removed in the product. It's often called the leaving group. For example, you've got this hydroxide here being substituted in for the bromide ion, and the bromide ion is a leaving group. Some examples of common nucleophiles include the hydroxide ion, cyanide ion, water and ammonia. Okay, a quick overview. We're going to predict the products, structures and names of organic products, and write the chemical equation for these substitution reactions. 1-chloropropane reacts with hydroxide ions. Have a quick go at that. Press pause. Have a go. Okay. Well, we've got that chloropropane there with a hydroxide ion. Let's highlight the things that are going to be substituted, which will switch out. Hydroxide will switch in for the chloride ion, and the chloride ion will be the leaving group. And we've got propant 1 all being formed. Okay, have a go at number 2. Press pause and have a go. Okay, we've got 2-bromo, 2-methylpropane reacting with the hydroxide ions. Let's highlight what's going to be switched in and switched out. And this is 2-methylpropane-2. And let's have a go at that last one. Press pause and have a go. Okay, we've got iodo-propane reacting with the cyanide ion. Let's highlight what's going to switch out, switch in. And we have butanylnitrile there. A nucleophile is just an electron-rich species which is attracted to a region of electron deficiency. A region of electron deficiency is present in halogenoalkanes. The carbon-halogen bond is a polar covalent bond due to the presence of the electronegative halogen atom. So electrons are shifting towards the halogen away from the carbon, resulting in a positive dipole on that carbon, and therefore it is an electron deficient region is created around that carbon atom. Nucleophiles are small particles that have a lone electron pair, and they may also have a negative charge, and they'll be attracted to that dipole. And as I said, some examples are hydroxide, cyanide ions, water and ammonia. An overview of nucleophilic substitution reactions. When the carbon halide bond, carbon halogen bond breaks during the substitution reaction, both electrons in the bond move towards the halogen atom. So you've got this bond here, and both electrons will go to the halogen atom. So it's heterolytic fission. And the halogen atom becomes a halide ion. And it's also known as the leaving group, as I've just discussed. The curly arrows. We're using double-sided curly arrows to show the movement of electron pairs when we describe mechanisms in organic reactions. So, breaking bonds will have heterolytic fission of the carbon halogen bond. Both electrons in the bond move to the halogen to form the ions. And so we use a double-headed arrow. The tail of the curly arrow shows where the electron pair originates, and the head shows where the pair goes. In this other example, forming bonds, attraction of the lone electron pair on a nucleophile to an electron deficient region forms a new covalent bond. The lone electron pair forms a coordinate covalent bond between the nucleophile and the carbon atom. So you can see this lone pair here, and both of these would go to form the bond. So it's going to be a dative bond or a coordinate bond. Looking at mechanisms again, you have rate determining steps. If there's two steps in the mechanism, in the process of the reaction, one will be slower than the other, and the overall rate of the thing will depend on the slowest one. So if we add them together, you can see it's just the substitution of the bromine and the hydroxide ion, just getting switched around, but there's two steps taking place. One step in every mechanism is the slowest step, and we call it the RDS, rate determining step. The rate of any chemical reaction depends on the rate of the slowest step in the reaction mechanism. You can't go faster than the slowest step. So the two types of nucleophilic substitution are 1 and 2. That's easy to remember. SN1 have one reactant in the rate determining step. I bet you can guess how many SN2 has. The rate determining step in SN1 is unimolecular, and it occurs in tertiary halogenoalkanes. SN2 obviously has two reactants, like I'm sure you did guess, and it's bimolecular. The rate determining step is bimolecular, and you'll see this in primary halogenoalkanes. The rate determining step is step 1 in both of the mechanisms. The SN1 mechanism, we've got tertiary halogenoalkane and a nucleophile. We've got 2-bromo-2-methylpropane here in dilute aqueous sodium hydroxide. There's obviously two reactants, as you can see there. We've got the hydroxide ion, the nucleophile, and we've got this. We've got the tertiary halogenoalkane here. You can see the bromine there, and you can see the positive dipole on the central carbon. Because it's a tertiary halogenoalkane, we get something called steric hindrance. The bulky alkyl groups, these bulky methyl groups in this case, block the direct attack of the nucleophile. The nucleophile couldn't get into this. These get in the way, so it can't attack straight away. And so something else takes place first of all. What happens is you get a breaking of the carbon-bromine carbon-bromine bond before the nucleophilic attack. So the electronegative bromine breaks off, and you get this positive carbocation. You get heterolytic fission. The bromide leaves, and this carbocation is formed, which, as we know, is stabilized by these methyl groups. And once the carbocation is formed, we then get nucleophilic attack. The hydroxide ion you can see here, which is negative, is going to be attracted to the positive carbocation in the center there, and we're going to get a bond formed between the two. So it approaches a dative or coordinate bond forms as the hydroxide ion donates a pair of electrons to form the new bond, and you get the final product. Okay, we've got to use structural formulas and curly arrows. We need to be able to do this, so let's see how we do it. We're getting steric hindrance in step 1, so where the nucleophile won't attack straight away, but a carbocation can form because we've got this electronegative bromine. It's going to draw the electrons to itself, breaking the carbon-halogen bond, getting this carbocation forming, which is trigonal planar. And we also get the bromide ion free. Next, the carbocation and the hydroxide ion will react. We're going to use our curly arrows to show the lone pair from the hydroxide ion donating to the carbocation positive center, forming a new bond. So it's a two-step mechanism. The first step is rate determining. You have to remember the role of steric hindrance, that the bulky alkyl groups around the carbon atom with the halogen prevent a direct attack by the nucleophile. The halogen must leave first, producing the stable carbocation, and it occurs in protic polar solvents, which are solvents that make hydrogen bonds. For example, water, alcohol, or carboxylic acids. This helps to stabilise the carbocation. Okay, you can have a quick go at that yourself. Please press pause, and it should be quite straightforward at this point. Next we go, I've gone too far. Next we can look at the SN2 mechanisms. Primary halogenoalkanes and nucleophiles. Look at the reaction of bromoethane in dilute sodium hydroxide. So the reactants, we have two things. We've got the bromoethane and the hydroxide ion. We've got this nucleophile with its lone pair, and we've got the primary halogenoalkane with that dipole, with the two dipoles, that polar bond. We get a nucleophile approach. In this case, the hydroxide ion is moving towards the bromoethane. It approaches from the side opposite to the halogen. It forms a transition state. The carbon-bromine bond starts to break at the very same time as the carbon-oxygen bond starts to form. So we'll get a transition state, and then after that the halide ion leaves and you get a new organic product, in this case an alcohol. The breaking of the carbon-bromine is a heterolytic fission. The halogen takes both electrons to form the negative ion. And so dative covalent bond forms between the carbon and oxygen bond. Let's have a look using structural formula and curly arrows. So we've got the hydroxide ion, going to substitute in for the chlorine. You've got the nucleophile approaches from the back opposite to the halogen, or to the leaving group. So we've got the bonds, the two electrons in this bond moving onto the chlorine, and you've got the lone pair from the hydroxide ion moving towards the carbon, which will be delta plus, positive dipole. And you form this transition state which will exist. It's very high energy and it's unstable. You see it's trigonal bipyramidal, and it won't hang around for very long. And the chlorine will get booted off, and you get an inverted structure as well. If you look here, you've got CH3HH on this side. Over here, it's inverted. It's a one-step mechanism, and it's called a concerted mechanism. There's an inversion around the carbon atom when the nucleophile attacks. So you've got the nucleophile coming in here, and the L gets booted off, and you can see we've inverted X, Y, and Z are inverted X, Y, Z. It's a bit like an umbrella getting pushed inside out. We use aprotic polar solvents for this reaction. Aprotic means solvents that do not make hydrogen bonds. An example would be propanone or ethane nitrile. They don't block the nucleophile from attacking. Okay, have another go with that one, please. And you can also have a go at that. So take your time, complete those two slides. Okay, so let's make a table of the key features of the SN1 and SN2 mechanisms. We'll look at SN1 first. The type of halogenoalkanes are tertiary. Number of reactants in the first step of the rate determining step 1. Type of intermediate that forms, we're forming that carbo-cation. Type of solvents, we need protic and polar solvents. And there's two steps to that mechanism. SN2 will have primary halogenoalkanes. There's two reactants in the rate determining step. We're making that transition state, which is unstable, and we've got aprotic polar solvents. There's one concerted step, which results in inversion. Okay, there's some factors that affect the rates of these nucleophilic substitution reactants. The type of halogenoalkane. We've got tertiary mechanism. We've got secondary. halogenoalkanes which can do both SN1 or SN2. As we know, tertiary only does SN1. We've got primary, which is SN2. The formation of the carbocation intermediate requires less energy, and this is why the rate of the SN1 mechanism is faster. So you can see here on our potential energy diagram, the rate progressive reaction, you've got a lower activation energy to get over with the carbocation, and so you're going to get a faster rate of reaction compared with the high activation energy required to form the transition state. When you've got that carbon which has 5 bonds, and it isn't going to like that very much, so you need more energy to get up there to overcome it, so it's going to be a bit slower. The formation of the transition state requires more energy. The type of halogen also affects the rate. Iodine being the fastest, fluorine being the slowest. A carbon halogen bond breaks during the nucleophilic substitution reactions of halogenoalkanes. The strength of this bond has an effect on the rate. So the weaker the bond, and for example carbon iodine bond is the weakest, so less energy is needed to break it, therefore it'll react the fastest. Conversely, the carbon fluorine bond is the strongest, requires more energy to break, so fluoroalkanes react more slowly. The type of nucleophile affects the rate of reaction. You see here cyanide is the fastest, then hydroxide, then ammonia and water, and you can probably see straight away that in general anions, we've got charges here and charges there, and these are neutral. In general, anions tend to be better nucleophiles than their corresponding neutral molecules because they have a higher electron density and are more readily attracted to a region of electron deficiency. Nitrogen containing nucleophiles are also better nucleophiles than those with oxygen. This is because their covalent bonds are less polar, so they'll donate their lone electron pairs more readily. You can measure the rate of SN reactions using silver nitrate. If you add silver nitrate to a reaction mixture, the silver ions will form precipitate when the halide ions are released. You can see here you can get silver chloride, silver boron, silver iodide, all solids, they will precipitate out. By measuring the amount of precipitate formed over time, the rate of reaction can be compared. Okay, SN mechanisms using different nucleophiles. Let's have a look at OH minus, the hydroxide ion. The general equation is a halogenoalkane with hydroxide gives alcohol and halide ion. For example, we use bromoethane with a hydroxide, you just switch them around. The hydroxide ion is present in dilute aqueous solutions. For example, sodium hydroxide and potassium hydroxide. The metal ion, potassium or sodium, is often emitted because it's just a spectator ion. The reaction occurs at room temperature. Water. The general equation would be the halogenoalkanes of water given alcohol and aqueous hydrogen halide. So you can see the hydroxide from the water switching in for the bromine. We're getting the hydrogen bromide. The aqueous hydrogen halides are acidic, and also you can think of HCl being a very good example of an acid. You don't need to know the mechanism for the nucleophilic substitution reactions or with water, which is nice, but you do need to know why the OH minus ion is a better nucleophile than H2O, and we know that because we just said before. They're being attracted to an electron deficient region with partial or positive charge. So the negatively charged ion is more strongly attracted to the positive region than a neutral molecule. So the rate of reaction will be faster with OH minus. With water, conversely, neutral molecule therefore has a weaker attraction to the positive region than an ion with a negative charge. So the rate would be slower. Okay, the nucleophiles water. What would be the equation for this reaction with water? We're going to just switch in the OH minus with a Br, aren't we? There we go. And then you can just write out the structural formula if you want to work out the name of the thing. And obviously it's 2-methyl butane 2O. So let's have a look at this. We've got for nucleophilic substitution with the hydroxide ion, the conditions are aqueous OH minus, and we get an alcohol and the halide getting booted off. With water, it just needs to be warm, and we get an alcohol, and we get the hydrogen halide. And you can see there's a nice big, not in the new syllabus thing there. We used to have to know about the nitriles and ammonia, and you don't anymore, which is just fantastic. And that's that for this presentation. Splendid. You may want to look at these 2 YouTube clips which show you those reactions taking place. They are fantastic.